met. The review class before the test. There were a good number of questions prior to me going into chapter 5, section 5.1. I'm not sure if we got as far as I did with one or two of the other classes. But if I remember correctly, we were at Dalton's atomic theory. So I want to begin on the bottom of 8 through 7. I am not interested in dates with any of this chronology that we talk about. What I am interested in is the sciences we focus on. You should be able to, in a reasonably succinct manner, explain what it is they did in terms of our understanding of the atom, because that's what sections 5, 1, 2, 3, and 4 are really all about. So it's more what they did than when they did it, okay? So although Dalton's atomic theory, albeit slowly, brought society back to the idea that had been suggested by Democritus more than 2,000 years earlier, it was just the beginning. And as far as Dalton was concerned, an atom was a tiny, invisible, indivisible sphere. And it could not be broken down into anything smaller. And one of the questions in the quick checks, which part of Dalton's atomic theory is now known to be incorrect? Basically the one that says that atoms cannot be, or the smallest particles, they can't be broken into anything small. So when we talk about subatomic particles, we're talking about things smaller than atoms. And the beginning of our understanding that atoms actually do have smaller particles began around the middle of the 1800s. And I mean, there's a long series of discoveries and people who contributed piecemeal to our understanding of the atom. We don't have time, nor is it that imperative that we would go through all of it. But if you look at the 5.1 activity, that's really just for your interest sake, okay? So the names of the guys I've listed in those 4 columns, and there are more, but those sort of collectively contributed eventually to our understanding of the atom. We're not going to talk about all of them. We're going to, the fact that you know they're there, we're just going to focus on a few. The relationship between matter and electric charge fascinated scientists in the 1800s. They wondered, for example, how electricity passed through matter, and how it passed through solids, how it passed through liquids, how it even passed through gases, and how it might behave in the absence of matter. In other words, was matter necessary for electric charge to be conducted? And the idea about electric charge really was not well understood at all. Indeed, until the 1880s, we didn't have any suggestion as to how solutions conducted electricity. And that was courtesy of a scientist named Arrhenius. And it was something he proposed in his PhD thesis, but most of the evaluating professors in that PhD defense thought he was a nutball. They thought it was ridiculous. So the other thing about our understanding of the atom, it did not come without resistance, which is often the way revolutionary ideas have to play out in the scientific community. And science is supposed to be like that. Science is supposed to challenge new ideas. And again, that's courtesy of Robert Boyle. Believe nothing until you can prove it to yourself. So it's not a bad thing. It's just that it's sometimes, when the ideas are actually correct, that level of scrutiny or skepticism sometimes sort of impedes the development that might otherwise happen faster. Between 1859 and 1879, work done by Julius Blücher in Germany and William Crookes in England, using special glass tubes, soon led to one of the most important discoveries ever made about matter and the nature of the atom. And I would argue that it led to the most important discovery of the nature of the atom. Not the structure, but the nature. One such device that William Crookes worked with consisted of a sealed glass tube connected to a vacuum pump. The vacuum pump effectively sucks out the atmosphere from inside the tube. The tube contained a negatively charged terminal called a cathode, and it's this little wire right here. And we call it a cathode. We talked about anodes and cathode in physics yet at all? We call it a cathode because that's, as we now know, that's where the cations go, okay? Embedded in one end and a positive terminal, an anode, located about halfway along the length. And this is the anode here. So that's the positive terminal. What you can't see in that diagram is the accelerating voltage attached to this. So you guys know, I don't know, from Science 9, you recognize that? What that is, the long lines, the positive terminal, the short lines, the negative one? Yeah, so in any event, the accelerating voltage was about 10,000 volts, okay? When a high voltage was applied across, and a broad flat cross sitting right here inside the tube. That wasn't connected to anything charged, it was just in the way, in the middle of that tube. When a high voltage was applied across the electrode as the air was pumped out, any air remaining in the tube began to glow by a phenomenon called fluorescence. And they kind of expected that. They didn't understand how, but they knew that charge could be conducted through the air. So one of the things that Crookes was wondering is, how much air do I have to suck out of here before no more conduction occurs? In other words, they thought the conduction of charge was a function of the air, the gas in the tube. And so they fully expected when the tube was evacuated, there would be no more glow coming from the tube. As they expected, then, the glow faded as the air was removed. But close inspection in the darkened laboratory revealed a shadow of a cross. So in other words, when all the air was gone, with the lights on, you didn't really see anything, but with the lights off, they saw a faint green glow coming from the cathode, and then a shadow of the cross on the opposite end of the tube. The location of the shadow, in other words, here, and the cathode's glow led Crookes to conclude that something must be traveling from the cathode to the other end of the tube, even though all the air was gone. And based on what he thought would happen, that contradicted it, because there was no air in there. So how could any charge be conducted? In Paris, Jean-Baptiste Perrin discovered that a magnet placed next to the tube was able to deflect the mysterious beam. Now, why is that important? Well, obviously Crookes wondered what this mysterious beam or ray was. And because it appeared to be coming from the cathode, it was appropriately dubbed a cathode ray. But Crookes didn't know if it was just energy or if it was particles, but Perrin knew that charged particles are deflected in a magnetic beam. Only charged particles. Light isn't. Because Perrin knew that only a beam of charged particles can be deflected by a magnetic field, he concluded that this mysterious cathode ray must be a stream of charged particles. So when he placed the magnet next to the tube, the beam was deflected. You guys haven't taken magnetism in any previous science courses, have you? We believe that all magnetism is generated by moving charges. So why does moving charged particles, are deflected by a beam, deflected by a magnetic field? because they have their own magnetic field. Anytime charges move, they generate a magnetic field. So the two magnetic fields are interacting with each other. So whatever this beam was, it had a charge and it had mass. And I can sort of briefly show you an example of that. None of you probably have the old types of televisions that were around in the 60s or 70s because you're too young. But what they used to be was basically a cathode ray tube. Okay? And the screen that you saw, what you saw on the TV screen, was a result of these charged particles heating a fluorescent coating. Okay? So this is a cathode ray tube. And there's a fluorescent coating on the inner surface of this. And once this thing warms up, I'll see if I can show you a little focused version of what generated that shadow of the cross and what Perrin was able to deflect. This is old, way older than you guys are. And the fact that it's been sitting at the back of the room, I can't guarantee that grade 8s haven't played with it and ruined it, but that's better. I'm hoping against hope that I can get this beam to focus on the fluorescent screen. It takes a bit to warm up. Now this isn't 10,000 volts, it's about 700. Yeah, it must have been knocked at some point because that little spot should be sitting dead center, and it isn't. But that's all right, I can still deflect it. You guys see that little green spot? If it was just a beam of light, I couldn't do that. And depending on which pole of the magnet I bring next to that beam, I can deflect it in different directions. Now there's nothing quantitative about that, that's just qualitative. That's effectively what Perrin did, okay? The fact that this happens means whatever's generating that thing has mass and charge, okay? Many researchers experimented with cathode ray tubes as they came to be known. And if you look over there, the box that it comes from, see that CRT, that's what it stands for, cathode ray tube. And if, in the old days when they had the old TVs, if you ever got a TV repair person to come in and fix your television, he or she didn't call it a television tube, called it a cathode ray tube, okay? And what was done on the old TVs is this little beam was made to scan across the fluorescent surface really fast in an ordered way. We call it rastering. You couldn't see it because it was happening too fast, but it generated the picture on the television screen. And that's like information consistent with the slide rule. You're never going to need to know that again. However, it wasn't until the great English physicist Joseph John Thomson turned his attention to these mysterious rays that a breakthrough came. In 1897, Thomson set to work to discover the nature of the cathode rays. He modified the original Crookes tube by passing the diffuse cathode ray. Diffuse means it's just all spread out. It's not spread out here because it's being focused intentionally. But what Thomson did was, and again, you can't really see it too well in the little diagram at the bottom of the page there, but I think I can improve that a little bit here. So, this little thing there is the cathode, okay? So that's the negative. This is the positive, so again back here, you had the accelerating voltage, negative, positive, and again, about 10,000 volts. So the first thing he did is he focused this diffuse cathode ray. The anode was this thing. Now it was a sphere, but in the center of the sphere, he drilled a little hole. So what you're looking at is that circle from the side. So that has a positive charge, but that's the hole through the center of the sphere. Then he focused it again. In other words, he wanted a very narrow beam or ray to enter his evacuated tube. At this end of the tube, he put a fluorescent coating because he knew that a fluorescent coating always glows when struck by a charged particle. But between this and this, he put an electric field. He wanted to find out what charge was on these things, but also get an idea of how heavy they were, their mass. So as you see here, the electric field, I don't know why it takes a while to set there. So the positive plate was here, negative plate was there. This wasn't high voltage. It didn't have to be high voltage. But the reason that he used an electric field instead of a magnet is you can vary the strength of an electric field. Thomson knew that the amount of deflection a charged particle experiences in an electric field depends on two things: the ratio of the particle's charge to its mass. And that's often abbreviated this way. The more charge relative to the mass, the more the deflection, okay? So the lighter the particle and the more the charge, the more it would be deflected, okay? The heavier it was and the less the charge, the less it would be deflected. So an analogy that might work is, let's say I have that fan. You guys all know that big annoying fan? Let's say if I turn that on and it's blowing this way, and I toss a golf ball into the stream of wind. Golf ball is going to move a little bit. But if I toss a ping pong ball in it, it's going to move a lot. So imagine that the velocity of the wind is the strength of the electric field. The little thing that goes in there, if it doesn't have a lot of mass, but it does have a lot of charge, it's going to go a lot, okay? The more charge and the less mass, the greater the deflection. So the larger the ratio, the greater the deflection. By carefully adjusting the currents in his modified vacuum tube, I guess I should erase the board here. Thomson was actually able to calculate the magnitude of that ratio. Not the individual mass or charge by itself, but the ratio. In other words, quantify something about this mysterious ray or beam of particles. Found it to be 1.76 times 10 to the 8 coulombs per gram. Now, that's the SI unit for charge. And so that's like 176 million coulombs per gram. Now, why was that number important? Because that was about 2,000 times greater than the charge to mass ratio for the hydrogen ion, which was the smallest particle known in 1897. The lightest atom is hydrogen. With a charge, it has a charge to mass ratio 2,000 times less than that. So that meant one of two things to Thomson. Whatever this beam of mysterious particles was coming from the cathode, it either had 2,000 times the charge on a hydrogen ion, and the mass was the same, or it had the same magnitude of charge, but the mass was only 1/2000th of the hydrogen atom. Do you guys see that those are the two possibilities? Either the charge on this thing is 2,000 times more than a hydrogen ion, or the mass of this thing is 2,000 times less. Because this ratio for this mysterious particle was 2,000 times bigger than for the hydrogen. Didn't make sense to Thomson that the charge would be 2,000 times greater. So the only other thing that made sense was therefore the mass had to be 2,000 times smaller. Thomson concluded then that the magnitude of the charge on these negative particles would equal that of the hydrogen ions, same magnitude but different sign, but that the mass of these particles was actually 2,000 times less than hydrogen ions. Now that was a revolutionary idea because remember, according to Dalton, there was nothing smaller than an atom. Thomson used a whole bunch of different materials for the cathode, and he got exactly the same results. Didn't matter what he used for the cathode. So whatever these mysterious little particles were, they were way smaller than an atom, and they were the same regardless of what he used as the conductor for the cathode. So these little things with a negative charge seem to be coming from the atoms in the cathode, and they were always the same. Thomson repeated his experiments then many times with different metals used as a cathode. All he needed was a conducting material. And even different gases inside the tube. It didn't make any difference. Each time the results were the same. This had to mean that these mysterious negative particles were present in atoms of different elements. And they were always the same in those atoms of different elements. In a speech given on April 29, 1897 at the Royal Institution, J.J. Thomson told his audience that cathode rays were actually tiny negatively charged corpuscles of electricity. That's the term he used. Each with an identical mass, and that mass was about 2,000 times lighter than an atom of hydrogen. The audience was largely skeptical, as the science community normally is, and reluctant to accept Thomson's radical assertion that bits of matter even smaller, and not a little bit smaller, but way smaller than atoms themselves existed. Soon, however, the revolutionary idea was accepted. What was the little tiny corpuscle? It's an electron, and showed to be a component of every atom. So what's happening in a cathode ray tube? Well, with 10,000 volts, we're literally burning electrons off the cathode. So that little green glow you saw were electrons being burned off the metal of the cathode, accelerated through the positive terminal, and then hitting the fluorescent screen. That's what he was seeing, electrons. In 1906, Thomson was awarded the Nobel Prize for his work on the conduction of electricity through gases, in which he discovered the negative charges that became known as electrons. In an article in England's Philosophical magazine in 1897, Thomson suggested what else might be in an atom. He knew that an intact atom had no charge. Then there must therefore be something positive in the atom to balance that negative charge, to cancel, if you will, the charge on the electron. He discovered that something within a few years. At this point, it's valuable to consider the significance of what Thomson discovered. First, he found that atoms were themselves built from smaller components, that is, subatomic particles. But more importantly than that, he found that these subatomic particles were charged, namely that an atom is an electrical entity. Remember that idea because it will be fundamental to most of the chemistry you'll ever learn. Without charged particles making up atoms, there would be no chemical reactions. There would be no chemical compounds. There would be no energy derived from chemical changes. You and I and nothing else would exist, were it not for the fact that atoms are electrical entities. Okay? All the charges, all the compounds, all the reactions, all stem from that. Okay? Thomson soon used hydrogen gas in a further modified cathode ray tube to demonstrate that atoms did indeed have a positively charged component. This led him to propose the first revision to Dalton's 1808 atomic model, which really was nothing other than atoms are tiny little indivisible spheres. 95 years after that, Thomson proposed what has come to be called the plum pudding model. According to Thomson, an atom could be seen as a spongy ball with negative electrons distributed evenly throughout a positively charged spongy mass, much like bits of fruit in an English pudding or raisins in a muffin. And the number of electrons that were embedded and stationary in that positive mass exactly canceled the mass of the doughy part, if you will. So this was all the positive part, okay? That was all positive. As many electrons as were required to neutralize that charge were embedded in that positive mass. Now, of course, we know that's not the case, but it was a dramatic departure from Dalton's model, and it took 95 years. The replacement to Thomson's model took 8 years, okay? And it was one of his students named Ernest Rutherford. Thomson's plum pudding model, as it became known, was soon replaced by other models, but it nonetheless represented a major advance in our understanding of the atom and of matter itself. And I would argue that Thomson's discovery of the charged nature of the atom is the most important discovery ever made about the nature of the atom. Not the structure, but the nature. Now, I wanted to put a separate section in the book about Robert Millikan. But Sherry and Meg said, no, that's too much. And I went, no, it's not. But then I acquiesced to avoid conflict. So I put it in a quick check. This isn't what I wanted to do, but I did it nonetheless. The electron's charge. So all Thomson was able to do, and I'm not saying all he was able to do by any means to minimize what he did. Thomson worked at a laboratory in Cambridge called the Cavendish Laboratories, named after a British scientist named Henry Cavendish. And if you got to study with J.J. Thomson at the Cavendish Laboratories at Cambridge, you were at the pinnacle of your career. Thomson was like the god worldwide of physics research at the end of the 1800s. And anybody that studied with him, including his son, was as likely as not to be awarded a Nobel Prize at some point. Okay, and we'll get back to that soon. But this is what Thomson was able to discover. Now, Thomson had ideas about how you could find the charge by itself. And obviously, if you knew the charge to mass ratio and you could find the charge, you could also find the mass of these things, these electrons. Thomson had an idea called the cloud method, and it was pretty complicated, and it was sort of fraught with variables, but it kind of worked in terms of an order of magnitude for charge. But the scientist that actually nailed the charge down was an American physicist named Robert Millikan. And in 1909, Millikan determined the charge on the electron to be this. Not the charge to mass, he figured out the charge. 1.602 times 10 to the minus 19 coulombs. So, if this is the charge to mass ratio, and that's the charge, what's the mass? And how about you give it to me in grams. And here's a clue. To determine the mass in grams, begin with the provided value of charge in coulombs and use the charge to mass ratio as a conversion factor. So, if you want this to turn into grams, flip that upside down. That charge times 1 gram over 1.76 times 10 to the 8 coulombs per gram. Flip that upside down, and then actually give the answer in kilograms. Give me the answer in kilograms, and you'll see why I'm doing this as a clever prelude to what we're going to be doing later on in the chapter. 2 decimal places if you want. Or 2 sig figs, not 2 decimal places, 2 sig figs. Nine point what? Times 10 to the what? Louder? 9.1 times 10 to the minus 31 kilograms. Now remember how hard it was for us to appreciate, wrap our head around how big Avogadro's number was? 6 times 10 to the 23. This is 100 million times smaller than Avogadro's number is big. So it's about 9.11 times 10 to the minus 31 kilograms. Why is that significant? Well, because when things get that small, they don't behave like we expect them to. Things this big do. Something that's big enough for me to pick up and look at does behave like that. If I throw this at that concrete wall, it's going to bounce off. If I step in front of a bus, I'm going to get hit and die. But things on the order of the really tiny, and we call that world quantum systems. That's what chemists refer to it as. It means damn tiny. Things don't behave like we expect them to. Particles don't behave like we expect them to. And the majority of our challenge associated with atomic structure was about these electrons. The rest of it we figured out reasonably well, but the hard part was describing electrons. And the problem is that if we treat them like particles, then all they do is argue with us. Because on the order of the really tiny, things don't behave the way we think they should. And that's kind of important. Because all chemical behavior is a result of electrons, 100%. So if we can't describe electrons properly, we can't understand matter. And that's really the problem that section 5.1 ends with, and section 5.2 attempts to solve. It's also the problem that 5.2 ends with, and section 5.3 attempts to solve. It's all about the electrons. Okay? They were the things that were the problem. And one way to maybe describe it is they weren't being treated with the respect they were due. The world is more complicated than just particles and waves. And at the end of the 1800s, the best physicists on the planet believed wave physics was here, particle physics was here, mutually exclusive. But as it turned out, literally at the turn of the 20th century, 1900, a discovery was made that maybe suggested, there might be some gray areas there. Maybe waves can behave like particles. And if that's true, maybe the reverse is true. And that's the clue to where we're going to get to in section 5.3. Okay? What evidence led Crookes to conclude the unknown ray in his vacuum tube originated the cathode? Because there was a glow coming from the cathode, and the shadow of the cross was on the opposite end of the tube. Duh. It was a beam of charged particles deflected by a magnet. Maybe a beam of negatively charged particles. Well, because the cathode was negative. And if something was coming from the cathode, traveling past the anode to the other end of the tube, maybe those serious things were negative. Okay? But again, it fell upon Thomson to quantify it. This is kind of optional. Identify the two most important components of Thomson's atomic theory. A, there are subatomic particles. And B, they have opposite charges. Okay? In 1895, young Ernest Rutherford, working on his father's farm in New Zealand, his father was a potato farmer, received the news that he won a scholarship to study at the University of Cambridge with J.J. Thomson at the prestigious Cavendish Laboratory. The Cavendish Laboratory, by the way, still exists in Cambridge. People sometimes get Oxford and Cambridge mixed up. If you wanted to go into politics, go to Oxford. You want to go into science, you go to Cambridge. Rutherford arrived at Cambridge in time to work with Thomson during the discovery of negative electric charges. Because remember, 1897 was where he basically discovered that. Not surprisingly, therefore, Rutherford fully believed in the plum pudding model of the apple. Thomson was Rutherford's mentor. And Rutherford was like esteemed throughout the planet. And some of you might be wondering, wait a minute, we're talking about physicists, this is chemistry. It's the same thing, you guys. It's the same thing. It's just we focus on different parts of it, okay? After training with Thomson, Rutherford went to McGill University in Montreal, where he devoted much of his time to studying the nature of the emissions associated with the newly discovered phenomenon of radioactivity, to which you also might wonder, why are we talking about that? I thought we were talking about atomic structure. Fair question. Stay tuned. So, radioactivity was discovered at the end of the 1800s by a man named Henri Becquerel. But they didn't understand the nature of the emissions. They seemed to be spontaneous emissions from elements, for example, like uranium. Madame Curie and her husband Pierre in Paris were doing a lot of work with radioactivity. And Curie is credited with discovering two more radioactive elements. Polonium, named after her native Poland, and radium. And she was fascinated with radium. And radium, a sample of almost pure radium emits kind of a cool greenish glow. And it's said that Pierre and Marie used to carry around little pieces of radium in their pocket because they thought it was so cool. Dangerous as hell though, which is too bad. They didn't realize the dangers of what they were doing. But Rutherford obtained samples of uranium from Madame Curie in Paris and shipped over to McGill because he wanted to study the nature of these mysterious emissions coming from these radioactive elements. Rutherford's work at McGill would soon give him all the tools he needed to test Thomson's model. Using samples of radioactive elements such as radium provided by Marie and Pierre Curie, Rutherford and Frederick Soddy discovered three types of emissions associated with radioactivity. Now, we're not going to go into the description of the experiment that allowed that to happen because we don't have time. But this is what they discovered. And you might remember this from Science 10. They didn't know what these things were, so as physicists are often given to do, they represented them with letters from the Greek alphabet. So the first three letters in the Greek alphabet are alpha, beta, gamma. So one of the emissions coming from these radioactive radium sources, they called alpha particles. These things penetrated a few centimeters of air, but were stopped by a thin sheet of aluminum foil. They were pretty massive, and they were going about 16,000 kilometers per second. Now, Rutherford didn't know it initially at the time, but they were actually helium nuclei. And when Soddy and Rutherford actually figured out what was going on, remember radioactive decay we talked about in Science 10? What happens when an element gives off an alpha particle? Is it the same element? The atomic number drops by 2, the mass number drops by 4. So anything that emits an alpha particle now has 2 fewer protons in its nucleus, ergo, it's no longer the same element. And when Soddy and Rutherford actually figured that out, Rutherford basically said, like, this is transmutation, but don't call it that. We'll be labeled as alchemists. Because that's what alchemy was exactly trying to do. And it was called transmutation. That's what they called it. They were trying to find a way to transmutate elements from one form to something else. And what Rutherford and Soddy discovered, that's exactly what radioactivity was. Elements were turning into different elements. Okay? And again, why does that relate to atomic structure? We'll get there soon. Another one of the emissions, beta particles. As it turned out, these were actually electrons. They're going a lot faster. Okay? And because they're going a lot faster, they penetrate a lot more. Penetrated a few millimeters of aluminum, but stopped by a thin sheet of lead. And then the third emission wasn't a particle at all, it was a gamma ray. Traveling at the speed of light, penetrates at least 30 centimeters of lead or 2 kilometers of air. Okay? At the speed of light. Why was this important? Well, Rutherford looked at this, at alpha particles, and decided that this would be a dandy way to test Thomson's atomic bomb. In 1909, Rutherford had returned to England and joined the University of Manchester. Working with Hans Geiger and Ernest Marsden, Rutherford decided to use alpha particles as a type of probe to assess the makeup of an atom. The experiment involved aiming alpha particles emitted from a radioactive source at very thin sheets of gold. Gold is the most malleable metal. You can hammer it into sheets literally a couple hundred atoms thick. No other metal will do that, but that's how thin these gold sheets were. And then observing where those alpha particles struck a fluorescent screen after passing through the atom. So remember, Thomson had used his modified Crookes tube and to observe what electrons did in a fluorescent screen. Alpha particles were also charged. So Rutherford knew that a fluorescent screen would glow when struck by alpha particles. So what he did is, and if you look at the diagram here on the left, he had a lead block into which he drilled a little channel. And then in that channel, he put a radioactive source. And then, you can't really see it here, but around that, he had a fluorescent screen. And he carefully measured where those alpha particles struck this fluorescent screen without the gold. In other words, he wanted to aim it. You can never predict when a radioactive source is going to emit a particle. But when it did, there was a flash on the fluorescent coating. And Rutherford carefully determined where that flash occurred. Then he put the gold foil in front of the radioactive source. Now, to understand what he thought would happen, let's say I have a AK-47, which shoots through trees, okay? You're on the other side of a tree about that big, and somebody shoots an AK-47, it will go through the tree and kill you. So let's say I hung a piece of raisin bread from the tree, and I stepped back here with my AK-47, and I shot right at the piece of raisin bread. You would expect that that shell would go through the raisin bread as if it wasn't there. There shouldn't be anything in a piece of raisin bread that should deflect a shell from an AK-47, correct? Okay. Rutherford had been a student of J.J. Thomson. Thomson was his mentor. And he firmly believed that the plum pudding model accurately represented the structure of an atom. Based on that belief, Rutherford fully expected that nothing in Thomson's spongy atom was capable of significantly altering the path of alpha particles traveling at 16,000 kilometers per second. All of the alpha particles should therefore pass through the gold foil, meaning the atoms of the gold foil, without deviating from their original path. If any deflection occurred, it would be minimal at best. The vast majority of alpha particles behaved exactly as predicted. The vast majority of the AK-47 shells would go right through the raisin bread, as if it wasn't there. But, I know this sounds like Gary, and this is a huge but. A few particles deviated through large angles, and a very few, about 1 in 20,000, didn't go through the foil at all, but rather bounced back. Rutherford wrote in his journal that it was quite the most incredible event that has ever happened to me in my life. Now, he was a little bit more extreme in his analogy. It was almost as incredible as if you had fired a 15-inch shell. You know what 15-inch guns are? That's the diameter of the guns, like on the USS Missouri, that shoots 20 miles and kills things, okay? Battlefield guns, okay? Heavy artillery. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So anybody that thinks that these scientists are kind of deadpan, unemotional, boring guys with white coats and pocket protectors running around their lab are sadly mistaken. He was excited as hell. This was, to say the most incredible event that ever happened to me in my life. Imagine how surprised he was. Kind of as surprised as you would be if you shot at a piece of raisin bread and had to do this, because it came back and almost hit you. That shouldn't happen. So clearly there was something in the plum pudding model that wasn't raisins or wasn't muffin. Nothing in Thomson's atomic model should be capable of knocking an alpha particle far off its course, let alone turning it around. Clearly the model of the atom proposed by Thomson needed a major revision, and Rutherford was able to do just that. Now, this is a terrible diagram, but this is the only one I could find that would fit next to the thing on the left, okay? According to Rutherford explained the results by suggesting that virtually all of the mass of an atom was concentrated in a very tiny, dense, positive structure. In the atom center, he called the nucleus. It was very tiny because only a very few of the alpha particles had found it. The vast majority of the atom was empty space. That's why the vast majority of alpha particles went through the gold foil as if they were going through empty space. They were going through empty space. But a very tiny number either struck a glancing blow or had a direct hit on something really tiny and dense and positive. He assumed it was positive, number one, because he already knew that electrons had a really tiny mass. And the alpha particles themselves were positive. So it made perfect sense that it must have hit something very massive and positive, but also very tiny. Surrounding this nucleus was a cloud of negatively charged electrons that accounted for all of the atom's volume, but virtually none of its mass. Rutherford calculated that the nucleus was so small to compared to the volume occupied by the surrounding electrons, that the vast majority of an atom was actually empty space. Although Rutherford's model of the atom resembled a tiny planetary system, with electrons orbiting the nucleus much like planets orbit the sun, which is what you often hear, and what most of the people walking the hallways believe. Rutherford himself wrote, "The atom has often been likened to a solar system, where the sun corresponds to the nucleus and the planets to the electrons. The analogy, however, must not be pressed too far." So he realized that simplistic as it was, and maybe reasonably helpful to kind of understand it, you got to be careful how closely you apply it. Now, how small was the nucleus compared to the volume of the atom? Well, based on the number of alpha particles that actually found it, Rutherford calculated that the volume of the nucleus was about 1/1,000,000,000th the volume of the atom. And that's why the diagram up here is woefully inadequate. So this isn't close to being accurate, okay? And again, the better analogy is take BC place and suspend a grain of sand halfway between the floor and the ceiling in the center of BC place. That's the nucleus. BC place is the atom, okay? Which means all matter is virtually empty space, because atoms make up all matter. Rutherford was responsible for perhaps the most significant contribution ever made to our understanding of atomic structure. Not the nature of the atom, that's Thomson, but the structure. And he received the Nobel Prize in Chemistry in 1908. As did a good number of the researchers that have said that worked with Thomson in Cadmus laboratory. Shortly after discovering the nucleus, Rutherford realized that his model explained the charge nature of the atom, but not the mass. In other words, there was something missing that should account for the mass. He believed that a neutral particle must also exist in the nucleus that added mass but no charge. More than 20 years later, James Chadwick discovered that particle, the neutron, just as Rutherford had predicted. Several significant changes to Rutherford's atomic model were still needed to explain electron behavior. In other words, the model was correct, but there's something about the electrons that didn't work, and I'll touch on that in a second. As Rutherford theorized, the atom is an entity whose tiny positive nucleus accounts for 99.97% of its mass, but only about 1/1,000,000,000th of its volume. The negative electrons moved rapidly within the available atomic volume, held by the attraction of the nucleus, and were they not moving, they would collapse into the nucleus. Table 512 is a simplified summary of the composition of the atom as we view it today. And this column is really what I've added since the warm-up, okay? This is the absolute mass in grams. And notice there's 9.11 times 10 to the minus 28 grams, 10 to the minus 31 kilograms outside the nucleus. And the neutron's actually a little heavier than the proton. Not much, but a little bit. And it's the amount that it is heavier than the proton pretty much matches the mass of an electron. So one of the things we believe is that neutrons are actually protons and electrons together. And that explains beta radiation, or beta emission, but that's a little far afield right now. Okay? So, what do we mean several revisions of Rutherford's model were needed? Well, I don't explain it here, but I'm going to introduce it here just because it takes us into section 5.2. Remember I said that at the end of the 1800s, classical physics had certain ideas about matter and energy. Okay? One of the provable, demonstrable truths in physics was that accelerating charges radiate energy. So for example, radio waves. If you take an alternating current, which has electrons changing direction at a constant rate, in North America that's 60 cycles per second, those charged particles changing direction generate radio waves. In other words, accelerating, and you guys that are in physics know that acceleration is a change in velocity, right? And because velocity is a vector quantity, it's not just change in magnitude, it's change in direction, correct? So if something speeds up or slows down, it speeds up or slows down, or turns, it's still accelerating, correct? Okay, so let's imagine Rutherford's model. According to Rutherford's model, electrons orbited the nucleus. So let's say that's the atom, there's the nucleus. Let's say there's an electron here orbiting the nucleus. If it's orbiting the nucleus, it's constantly changing direction, correct? So as it's changing direction, it's accelerating. Well, according to classical physics, an accelerating charge radiates energy. Why is that a problem? Because if this thing radiates energy, any energy, it slows down. And if it slows down, it instantly collapses in the nucleus. Which means all matter goes back to being not empty space. It effectively collapses. Now, Rutherford knew this. He was a physicist. And he couldn't explain why this didn't happen. He was actually ready to abandon his model. Okay? And that's the problem that 5.1 ends with. According to classical physics, the Rutherford model shouldn't exist. It should collapse. As it turns out, he was right. There wasn't anything wrong with his theory. It's just the physics of the day had to catch up. And the scientists had suggested a way of saving Rutherford's model. It was a scientist who actually worked with Rutherford at the Cavendish Laboratory, a young Danish physicist named Niels Bohr. And that's what section 5.2 is about, okay? Before we do that, though, I know it's hard to wait because it's exciting, but we're going to do a little bit of quantitative chemistry here, okay? We can use the above table, that's the one with the protons, neutrons, and electrons, to discuss three important numbers associated with every element. And you saw these last year in Science 10, albeit briefly. The atomic number, usually designated as Z of an element, equals the number of protons and the positive charge of the nucleus. It also dictates the number of electrons orbiting the nucleus. And that's why it is the most prominent number in any element's space in the periodic table. The atomic number defines an atom. All of the atoms of a given element have the same atomic number, and each element's atomic number is different from that of every other element. For example, as you know, 6 protons in a nucleus make it carbon, 7 make it nitrogen, 8 for oxygen, and so on. This illustrates an extremely important point to remember. It's the number of protons that determines the identity of an atom. While the number of neutrons may vary in atoms of the same element, the number of protons don't. And should the number of neutrons vary, the different versions of that atom, as you know, are called isotopes. And depending on what the neutron number is relative to the proton number, sometimes we have radioactive isotopes or radioisotopes. Those are unstable nuclei. The presence of neutrons in the nucleus also contributes to the mass of an atom. And one of the roles we believe neutrons play is they help to hold the nucleus together. Does it seem contradictory that a nucleus would actually stay together? Well, you know it's really tiny, but what is it made of? Protons and neutrons, right? What's the only element in the table that has no neutrons? Hydrogen. Ever wonder why that is? Now, there's rare forms of hydrogen called deuterium that have a mass of 2, or tritium with 2 neutrons. But why does the vast majority of hydrogen have no neutrons? And why is it the only element that doesn't? Well, how many protons are in the nucleus? 1. As soon as we put more than 1 proton in the nucleus, we need neutrons. Why don't protons fly apart? They're the same charge. Why don't they repel each other? Well, they do. until they get really close. Until they get within 10 to the minus 10 meters, they repel each other. But when they get that close, which is the case in the nucleus, there's a force called a strong nuclear force. Carl Sagan described it as a little hook. And as soon as you get that close, they stick together. But we believe that neutrons roll, and some scientists call them gluons. They actually help that proton combination stay intact. And the more protons we put in the nucleus, and the bigger the nucleus becomes, the bigger the distance from one end of the nucleus to the other. And if that distance increases, then the nuclear force is harder to keep that nucleus together, because they're not as close together. And that's why we need more neutrons in it. So as the atomic number goes up, the neutron number increases. So for little atoms like carbon or nitrogen or oxygen, carbon 6 of each, nitrogen 7 of each, oxygen 8 of each. But when we get much bigger than 20, the number of neutrons increases more than the number of protons, until we get to the biggest naturally occurring element, which is uranium. Uranium has 92 protons. Nothing bigger than uranium exists in the universe, naturally. Anything bigger than that is synthetic. We made it, okay? But with 92 protons, it's got an atomic mass of 238. There's way more than 92 neutrons in uranium. But even with all those neutrons, it's still a radioactive element. And because it's such a big nucleus, nothing bigger than that exists in nature. And anything bigger than that, which we made, comes apart very quickly. It's just too unstable. Okay? Now, uranium isn't the only radioactive element, but that's what happens when atoms get big. It also happens when the number of neutrons relative to protons isn't quite right. And you might remember from Science 10 we talked about carbon-14. That has 8 neutrons and 6 protons. That's too many neutrons. That's a radioactive nucleus. Okay? Now, I get kind of far afield, but whatever. The presence of neutrons in the nucleus also contributes mass. The mass number then, normally designated A, is not the mass of the atom, it's the mass number. It's the number of protons plus the number of neutrons. Okay? And that goes here. So in standard atomic notation, there's the element symbol, there's the atomic number, there's the mass number. And the mass number is the sum of the protons and the neutrons. So obviously, pretty easy to determine the number of neutrons. Subtract this from this. That's the number of neutrons. Okay? Now how do you determine the mass number? The atomic number is on the table. But what if you have a mass in the table that's a fraction? Why would it be a fraction? We talked about this before. For example, look at chlorine's mass number. 35.453, and your table is 35.45. The only thing that contributes mass are the protons and neutrons. How do we get a fraction?
It's an average between all the isotopes.
Yeah. There are no fractional protons and neutrons. About 75% of all the chlorine that's there is chlorine 35. It's got to have 17 protons or it isn't chlorine, but it's got 18 neutrons. So if you take 75.75 times 35, the rest of the chlorine, about 25%, is chlorine 20. Okay? Sorry, chlorine 37. It's got 20 neutrons. So take 0.25 times 37 plus 0.75 times 35. And what do you get? You get 35. So how do you decide what the mass number of chlorine is? Well, usually round it to the nearest whole number. So for example, round that to 35. That means most of the chlorine out there is got 17 neutrons. Or sorry, 18 neutrons. Bromine, round it to 8. 79.9, that means most of the bromine has 80 minus 35, that many neutrons. That's the idea. But some students think that the mass number is the mass. It's not. It's a whole number. That's the sum of the whole number of protons plus whole numbers of neutrons. Using this notation, we can see that the neutron number can easily be calculated. Mass number minus the atomic number. So for example, the most stable form of nitrogen, known as nitrogen 14, because that's the mass number. Anything with nitrogen has 7 protons. But if we call it nitrogen 14, we're also saying, okay, well that has 7 neutrons. Fluorine 19, that has 10 neutrons. An atom's atomic mass is measured relative to an atomic standard, and we know what that is. The modern standard is a carbon-12 atoms whose mass, as we know from the mole chapter, is defined at exactly 12 atomic mass units. Therefore, one atomic mass unit is exactly 1/12 of the mass of a carbon-12 atom. Okay? Atomic mass, though, is the average mass of the element's atoms if you want a weighted average of the naturally occurring isotopes. Chemical changes never involve change to the nucleus, but involve electrons being added to or removed from. So in the same way that we can use standard notation for atoms, we can use standard notation for ions. So there's a magnesium atom, magnesium 24, which is the most common form of magnesium. There's a magnesium ion. Obviously, if that's 2+, it can't have 12 electrons. It's got 12 electrons if it's a neutral atom, but that only has 10. For every electron an atom gains, it also gains that amount of excess negative charge and becomes an anion. Each electron lost by an atom leaves that amount of excess positive charge on the resulting positive ion, or cation. So in other words, you should be able to indicate the number of protons, neutrons, and electrons for using standard atomic notation for ions as well. Okay? So obviously a phosphide anion doesn't have 15 electrons, it has to have 18. And a magnesium 2+ cation can't have 12 electrons, it's got to have only 10. Now that's effectively science 10, but what the heck. Atomic number, mass number, and neutron number. Determine the number of protons, neutrons, and electrons present in a 4+ ion of lead 207. And there's the standard atomic, or in this case, cation notation. Okay? So, the number of neutrons, if it's lead 207, 207 goes here, 82 goes there. You go to the atomic number, it's got to have 82 electrons as an atom. But as an ion, it has to have 4 fewer than 82. So if it's got a 4+ charge, it can only have 78 electrons. There's the notation, but that tells us that it can't have 82 electrons. And I put a few in here for you. Determine the number of protons, neutrons, and electrons present in each of the following. What about a telluride anion? Well, there's the number of protons, 52. 128 minus 52 is the number of neutrons, whether it's an ion or an atom. But if it's got a 2- charge, it's got 54 electrons, not 52. Which makes sense, because tellurium is too short compared to xenon. Not really too difficult. I've asked you to do for number 2 the atoms. So gold 197. 197 is the mass number. I don't have to specify the atomic number in this because gold always has the same atomic number. But 197 tells us the number of protons, which I get off the periodic table, plus the number of neutrons. So that's the mass number. So if you look at gold, it's got 79 protons. So you write gold, 79 goes here, 197 goes up here, 197 minus 79 is a number of neutrons. So, if the notation, if we want to do gold 197, there's gold. It's gold, so it's got 79 protons. 197 means protons plus neutrons equal that number, that minus that is the number of neutrons. And if it's an atom, it's got 79 electrons. Nothing to it. And just because it is so easy, and because I like tables, here's a table. So if there's no charge, then you can fill everything in. Atomic number is that, mass number is that minus that is the number of neutrons. That is always the same here. So those are always the same. Atomic number, number of protons, always the same. Number of electrons, if there's no charge, it has to be 42. If you see something like this, find 34 in your table, that's the element. If it's got 36 electrons, you can't be an atom. And if you look at the periodic table, you see that selenium has an atomic number of 34. As soon as you know this, you know it's selenium. If it's got 36 electrons, then it's gaining 2 to be like krypton, as you might expect. You should be able to take it from there. Okay? Yep.
If it's a multivalent, like there's different charges, what would you rate for the charge beside the atomic
Well,
rotation?
the charge would be specified. If the
Oh,
number of
okay.
electrons doesn't match the number of protons, you know the charge,
Okay.
okay? And if the charge is given here, then whether it's multivalent or not, there's the charge, okay? You guys okay with that? That's not hard, is it? No. You might wonder, however, how do we know what the masses of these things are? In other words, how do we know that isotopes exist in the first place? And if they do, how do we know what mass they are? And not only what mass they are, but how much of them are there? So in other words, I say, 25% of the chlorine that's out there is chlorine 37, 75% is chlorine 35. How do we know that? How do we know that there's chlorine 37 and that 25% of it is that? Although all the nuclei of the atoms of a particular element have the same atomic number, they may not have the same atomic mass. Again, courtesy of Science 10. Isotopes are different forms of the same element with different numbers of neutrons and therefore different mass values. For example, 98.89% of naturally occurring carbon atoms have 6 of each. 6 protons, 6 neutrons. They gotta have 6 protons or they're not carbon. 1.11% is carbon 13. And fewer than 0.01% is carbon 14. Carbon 14 is radioactive. And as you may or may not remember, it decays via beta emission to stable nitrogen 14. But the point is, how do we know that? Where do we get that info from? Remember that the chemical behavior of a particular element is determined primarily by the number of electrons. The atomic number of any neutral element equals the number of electrons surrounding the nuclei, so all of the isotopes of a particular element have almost identical chemical properties. The number of naturally occurring isotopes of an element and their relative masses and abundances may be determined by a device called a mass spectrometer, an instrument based on the same principles employed by J.J. Thomson, namely that the amount of deflection a charged particles experiences in an electric or magnetic field is a function of its charge to mass ratio. Mass spectrometry uses the fact that charged particles moving through a magnetic field are deflected from their original path based on their charge to mass ratio. The greater the ratio, the more the deflection.
Good morning, staff and students. A reminder to please keep Brother Bassett in your prayers. As a faith and learning community, let us prepare ourselves for the morning prayer. In the name of the Father, the Son, and the Holy Spirit. O God, we thank you for the life of Edmund Rice. He opened his heart to Christ, present in those oppressed by poverty and injustice. May we follow his example of faith and generosity. Grant us the courage and compassion of Edmund as we seek to live lives of love and service. We ask this through Christ our Lord. Amen. St. Thomas More, Blessed Edmund Rice, live Jesus in our hearts. In the name of the Father, the Son, and the Holy Spirit.
So for Wednesday, I'll give you your test back, but could you also read to the end of the section, and there's like a page and a half, and try the practice problems on page 245.